Let's see what's going on with our camera here. Have some problems. There we go. All right. We're going to do the last topic in the torsion section. So there are only the 3 little topics for torsion. That's why the last third of the course isn't just torsion. There are actually several little topics: torsion, pressure vessels, stress concentrations. I think that's most of it. And so what we're going to do right now is the last part of torsion. So the first part was torsional shear stress. Second part was angle of twist, and now the last part is power transmission. So it's the one that looks the least like statics, as far as things aren't moving. So the shaft is going to rotate now. So it is spinning, but it's not like translating anywhere. So we're talking still about circular shafts. They could be hollow tubes or solid shafts, rods. But we're not going to do prismatic cross sections like hexes or something like that. And we're going to talk about how that might be connected to a motor, an input source somewhere, and then connected to some sort of output. And that's kind of what we're going to do today. And let's start with, well, let's just go over a review of kind of the different equations we've used so far, so that we can make sure we're on the right page with that. So we've done, like I said, torsional. Well, let's do this. Oop, whoops. Oh, hold on. It's acting a little bit inconvenient today. I write on the screen with a pen, but it's also a touch screen, and if the touch part is not turned off, then it makes it really hard to write on there. So I'm going to see if we can reset it to turn off the touch part. It's old and it gets a little contrary sometimes. So let's see if that did it. It did. Excellent. All right. Now we can do what I wanted to do. So the 3 things we've done, or well, the 2 things we've done plus the 1 thing we're about to do. So we started with torsional, and I'm going to specify shear. This is a shear stress when we're talking about torsional stress. And we had an equation, tau. So it is going to use the same Greek letter tau that we used for shear stress before, but a different equation. So the equation we're going to use is T times rho over J. So hopefully you remember what those are. The capital T is the internal torque that particular section of our shaft is dealing with. Rho is, a lot of times, it's the outer radius, but it doesn't have to be. That's just where the maximum shear stress occurs, torsional shear stress occurs on the surface of the shaft. But you could calculate the torsional shear stress anywhere in the shaft by putting any number in for rho from the 0, where it's at the center, but if you put a 0 in, you get no shear stress, out to the radius. And then J is the polar moment of inertia, which has to do with the shape of the shaft. And again, we're only dealing with circular shafts. All right, so we did that. Then we did angle of twist. And that one we had theta. Theta was the angle of twist. This is how far a point on the surface of the shaft would move in a, along the shaft. I'll have to draw a picture, but how far it would twist if the shaft was undergoing torque enough that it would twist to some amount. So theta equals, again, that internal torque the section of the shaft is dealing with, the length of that section of the shaft, the polar moment of inertia of the section of that particular section of the shaft, because different, you could have a step shaft where one piece has a certain polar moment of inertia and another piece has a different polar moment of inertia, and then TL over JG. So G was the modulus of rigidity, where that is similar to the modulus of elasticity. So it talks about a shaft, in this case, not wanting to twist based on the material being not as ductile of a material, we'll say. And the units on this thing come out to be radians. When you plug in T, L, J, and G, you get a unitless number, which is understood to be radians. So if you wanted degrees, you'd have to convert that over. And then the new thing is power transmission. And I'm going to write the equation for power here. Power equals torque, well, not power, times. Power equals torque times omega. So again, it's the torque in that section of the shaft. And then omega is the angular velocity, so radians per second. I'll go ahead and write that down. So a lot of times when you're talking about a shaft spinning, you aren't using, like if you're just talking about it, you're not probably using units of radians per second. So a lot of times you're using RPM, so revolutions, not radians, revolutions per minute, or maybe hertz, cycles per second, so a revolution per second. But a lot of times you're not talking about radians per second. So we will have to make sure we convert over to radians per second when we're actually trying to get a value for omega. Oh, and that's not W. That is my version of lowercase Greek letter omega. All right. So let's do a little to develop our power. Oh, you know what? Before I forget, I was going to show you a little diagram for that angle of twist. I had already forgotten that. Let's see. Let's move this down. So angle of twist. Didn't want that to be an oval. Let's make it more circular. There we go. Angle of twist would be, let's say that we have point A here. We apply a torque, and we're not talking about this torque spinning this shaft here. This torque is twisting the shaft. So point A, after the torque is applied, moves down to here, we'll say, because the shaft has twisted. And this angle, however far it swept through that angle, that is the angle of twist. So it's not a rotation, it's not spinning. It is an angle of twist. And you can have both. You can have a shaft that is spinning and twisting at the same time. So just because we're about to talk about power transmission where the shaft is spinning doesn't mean that you don't also have angle of twist. That might seem weird that it could spin and still twist at the same time, but it's possible. All right. Now let's go back to our power transmission. Let's start actually without thinking of shafts. Just have a ground. Oh, let's try and get the ground more level. There we go. So this is just a ground surface. And we are going to put a box on this ground. Okay, there's our little box on the ground. And we're going to push with some amount of force on this box. And push hard enough and the box will move. So let's say it moves to over here. I wonder if I can... Oh, that's a really big eraser. Can I make a smaller eraser? Yes. Alright, so let's make a dotted line here so that it's a new spot. We'll see. There we go. So we've moved the box over here. We pushed on it enough that we moved it some distance. Let's put a distance in here. We'll just go from this corner over here. From that corner to that corner, we have moved it some distance, D. Okay, so that seems fine. If we wanted to calculate the amount of work we did, work is equal to however much force we applied and however much we moved the box. So work equals force times distance. So work equals, in our case, I've got F times D, right? Now that's not power though, so we do have to make sure we've got all these terms here: power, energy, work, all these force, all these different things. So work is applying a force over a distance. So I've actually done work when I moved the box, but depending on how fast I move the box will calculate how much power I generated. So if I move it really slowly, it takes me all day to move the box pushing on it, then that's a different amount of power than moving the box in 1 second. So it takes more power to move it faster. So in fact, power is equal to the amount of work you do divided by how long it takes you to do that work. Okay, so if I wanted to do power here, power equals work, which is force times distance, over time. We'll just use T. Let's put this in parentheses so it's not D over T. There we go. So that would be how we do power. But this is for sliding a box. So let's take this same idea and let's spin a shaft. So let's go over here and here's our shaft, the end of our shaft. And let's say that we've got a little box here on the surface of our shaft. That box could be a piece of the shaft. And we're going to apply force to it. But instead of it sliding on the flat ground that I drew the first time, it's going to move around the arc here. So it's going to go, around here. Let's just go to right there. And again, this I'm showing a box on the surface of the shaft, but it could be a piece of the shaft itself. This box could be part of the shaft. So that part's not particularly troublesome. So here, let's see, somewhere right in there is the center. That's the radius. And this path is an arc length, where arc length is, let's just finish this out here. We'll call this alpha. Arc length is the radius r times however far I swept through what I called alpha. So alpha, r times alpha. And that's just calculate, that's the definition of how you calculate the arc length. So in this case, the r alpha, that's the distance I moved. And F, I still applied some force F. Now, in a shaft, I might have applied that through a gear tooth, or maybe through a belt, or pulley, something like that, a pulley on a belt. So I might have applied the force differently than how I did when I pushed on the box. But I applied the force through some connection that this shaft has with other parts of the world. So let's do our same thing. Work equals force times distance. Let me just check my chat here, make sure nothing's, okay, good, nothing's in there bad. Sometimes I forget like to turn the microphone on or something, so and I didn't have it visible. So now we're good. Work equals force times distance. So here the force is still F, and the distance, instead of being just D like it was up here, now the distance is this arc length, which I have an equation for that says R, sometimes it's R theta, but I didn't want to use theta because we're already using theta for angle of twist. And this is not talking about it twisting. This is the shaft is spinning. It's freely moving in this one. That's why I used alpha. So R times alpha. Okay, and now I've got F times R. That looks familiar. And if I look at here, F is this force, R is this radius. I've got a force applied at a radius. That is the same thing as torque. So F times R becomes just torque. So the torque that's applied to this part of the shaft times alpha is the amount of work I've done. And then we still have the same definition of power being work that you do over some amount of time. So power equals T times alpha over, we just call it T, lowercase t for time. And this degrees per time. So if time is second, or well, radians, it could be radians that I measure alpha in. Radians per second, that is omega, angular velocity. So that's where my power equals torque times omega equation comes from. So if we need to calculate the power that's being transmitted in our shaft, we need to know how much torque it's dealing with and how fast it's spinning, basically. We just need the speed, the spinning of the shaft, to be in radians per second. Now, if you're using MathCAD or something like that, then it will handle it for you, and you don't have to manually convert. But if you're working out on paper, then we will have to manually convert whatever RPM or hertz that we're given over to radians per second. So let's do an example. Let's go here. And this is optional 3, problem 7. Looks like a really straightforward problem. Let's work that. So it's just a word problem. It doesn't even have a picture that goes with it. See if I can. Oh yeah, my shortcut key for that doesn't work. We got to do it this way. There. And paste this guy in as a picture. All right, so we have, this is, it even says simple horsepower. Oh, yes, horsepower. So the power that this is going to generate, T times omega, that's going to be torque, maybe inch-pounds, omega, radians per second. So you're going to get something like inch-pounds per second. Or it might be Newton-meters per second. So those are not horsepower. But when you're talking a lot of times about the power of an engine or a motor, it will often be given in horsepower. So we will have to convert, and that's a conversion that you'll just have to know. You'll have to know how to convert inch-pounds per second or foot-pounds per second over to horsepower. And there's no way to derive that. I'm not even sure exactly where it was first determined how much a horsepower is. I mean, it literally has to do with the power that a single horse can generate. It would be similar. This is probably not how they actually determined the number, but it would be similar if you had a well and a horse, and he's got a rope tied to the horse, and the rope goes over down into the well, and at the end of the well there's a pound of weight, and you make the horse move ahead so that the weight moves up an inch every second, and you could figure out a horsepower that way. I don't know that that's what they actually did. They probably just had some roundabout way of saying, well, a horse can do about this much. That's something maybe I should look up someday and see what did they actually do to figure out what a horsepower is. But let's just tell you for now, 1 horsepower, so HP is horsepower, equals, let me get it right, 550 foot-pounds per second. So in our little horse example, if you had a 550-pound weight down in the well that the horse is connected to, he could lift that a foot every second. So just by walking forward, the rope pulls the weight up. It's 550-pound weight. He can lift that a foot every second. So that, or same thing, 6,600 inch-pounds per second. So that's just 550 times 12 because you're just converting feet to inches. All right, so that's something you'll just have to know. There's not going to be another way. It's kind of like you'd have to know the amount of inches in centimeters. And that's also just a definition. I don't know if you knew that or not, but they're just defined to be an inch is 2.54 centimeters. That's just defined to be. An inch also kind of arrived from the not connected to centimeters. I think it was maybe sometime in the 1970s or so. I'm not certain on that, but sometime in that time frame, it was just decided that, well, we've standardized an inch now, and it's pretty close to 2.54 centimeters, and let's just make that the case. 1 inch is 2.54 centimeters. But a lot of the U.S. units were built around things that you either had, like a foot, or the length of an arm, or something like that, and then later on standardized. That's a whole another topic. If you take basic measurements, there's a whole other thing around standardization of these measurements, because it starts to become really important later on when you need mass manufacturing and things like that, where the part I made has to fit with the part you made. We need to be using the same unit system, and my inch can't be different from another person's inch if I'm expecting these parts to work together. Whole other thing. Just for now, know that a horsepower is this definition. All right. Our question says determine the horsepower. That's why we needed to know what horsepower was. That a 5-inch diameter shaft can transmit at 210 RPM. So that RPM, just so we're 100% sure what that means, RPM is a revolution per minute. So the shaft is spinning 1 revolution every minute. Actually, this one is spinning 210 revolutions every minute. If the maximum shear stress in the shaft is limited to 11,500 psi. Okay, so we've got a couple of things going on. One, shear stress. That's our tau equals T rho over J. So let's write that down. They said, just part of the problem statement, that tau, well, let's see, shear stress in the shaft must be limited to 11,500. That is tau. So instead of calculating tau, we're just going to put a number in, 11,500 psi. I'm going to write it as pounds per square inch, equals T. Now, we don't know T. In fact, that's what it wants to know. It wants to know horsepower, so we don't know T yet. Rho is since this is maximum worst case scenario, the maximum worst case shear stress is on the surface, and it does say that we have a 5-inch diameter, so that means rho is 2.5 inches because it's a radius. Rho is a radius, not a diameter. And if you see the letter C in place of rho, so you have TC over J, that means the outer radius also. Rho technically could be any number between the inner 0 out to the surface, but C is the outer radius. And then J doesn't say anything about this shaft being hollow, so it's going to be a solid shaft. We'll use pi over 32 times outer diameter, 5 inches, to the 4th. And so that J value is, remember, just so we don't forget, J is equal to the polar moment of inertia. And that's also equal to the integral of rho squared dA, which is the second moment of area, second polar moment of area. So you could take your cross section, the circle that is the cross section, and integrate it using integral of rho squared dA and figure out what J is. We are only dealing with circular shafts, so J is always going to be, for us, pi over 2 times c to the fourth minus b to the fourth. So in that case, that's for a hollow shaft. So we've got I don't know if I can get, and good enough. So C is the outer radius. We already said, oops, didn't want to do that. So C is the outer radius, and B is the inner radius. So if you have a solid shaft, B is just 0. I used pi over 32 because I was using the outer diameter. So outer diameter to the fourth minus inner diameter to the fourth. That's just a more convenient equation a lot of times, because if you have a shaft, you're probably referring to it by its diameter, not by its radius. All right, so based on what we have here, so all of this is just kind of an aside on how to deal with polar moment of inertia. We only have one unknown in that equation, and it's T. So we can solve for the amount of torque that this shaft is going to be able to deal with, the maximum amount, because that's what we're trying to solve. Determine the horsepower, the maximum amount of horsepower that this 5-inch shaft spinning at 210 RPMs is going to be able to deal with if we have a limit on the shear stress. So this equation will tell us the limit on the torque that it can deal with. So torque, therefore, torque equals, I need my calculator. Let's see. So we've got 11,500, and we're going to have to divide that by 2.5, and then we're going to have to multiply by pi. Then we're going to have to divide by 32. Then we're going to have to multiply by 5 to the fourth. Okay. And that would give us inch pounds. So if I did that right, 282,252.5 inch pounds. Divide by 12 if you want to know foot pounds. 23,521.04 foot pounds. Those are big numbers. But it's also a 5-inch diameter shaft, so that's a really big shaft. I'm going to run through the numbers just one more time just to make sure that we did it right. Let's see. Well, now I get a little bit different number. What did I do differently? 11,500. All right, so I think I just typed something wrong the first time. All right, so, or the second time rather. All right, so those look like our torque. So that's the amount of torque that this shaft can handle under our constraint. The constraint we're working with is in the problem statement. It says we're limited on the shear stress, torsional shear stress. Now, we wanted to figure out the horsepower, so the power, if this shaft is dealing with this torque, this huge amount of torque, 282,000 inch-pounds, and spinning at 210 RPM. So let's go over to that part. Power equals torque times omega. So in this case, we do want to solve for power. How much power can this shaft deal with? The torque is 282,252.5 inch-pounds. And then remember, we want radians per second here, but we're given 210 revolutions per minute, right? Let me make sure that's the right number. 210, yes. So I need to convert those revolutions per minute over to radians per second so that power will come out in inch-pounds per second, and then we can convert to horsepower because the problem specifically wanted horsepower. 1 minute is 60 seconds. So now I'm in inch-pound revolutions per second. I need to get the radians in there. So that means 1 revolution is 2 pi radians. And that'll get me radians per second times inch-pound. So inch-pound per second, which is what I want. So let's see what that gives me. 282,252.5 times 210 divided by 60 times 2 times pi. 6,207,056.7 inch-pound per second. You don't normally write the radians in there. Remember last time we defined what a radian is, and it's just a ratio. So we're not gonna put radians in our equation. We just need radians to be the units because revolution is not a ratio, it's a quantity. So revolution is different from radian. All right, but we want horsepower. Go back up to our little conversion. We have inch-pounds per second, so it takes 6,600 inch-pounds per second to make 1 horsepower. So let's divide this number by 6,600. And we get, where's the decimal? 940.5 horsepower. So in the end, that's not crazy. 900, that seems actually kind of small. Did I do that right? Let's check web work, see what it says. No, it's right. All right, so 940.46. I have 940.463. So we actually have a very similar answer. That seems a little small, but I guess we're going kind of fast. 940 horsepower is not crazy amount. Actually, I guess the limit here, why it seems small, is we're limited to a relatively low shear stress. So that's a softer metal, like just a generic steel would be in this range, a little bit higher than this. So we have some factor of safety included, but this is not a super high hardened shaft or anything. All right, so that's that one. Let's see if we've got another one here we can work. That one is very similar, except instead of starting with the shear strength, tau equals TC or T rho over J, this one has the limiting thing as angle of twist. So you would just start with theta equals TL over JG, solve for theta, or solve for T, and then plug T into power equation. So this is very similar to what we just did. I don't think we'll do that one. This one's got some new stuff in it. So this one has like some gear ratios. Let's do this one. All right. This one actually has several things going on, so I think it will be a good problem. All right, so let's make sure that you're looking at the same thing. Yes, you are. All right, so we've got a motor. So this is like a AC or DC motor. Looks at that size is probably an AC motor, alternating current. It is a 100 horsepower motor, so it's a bigger, beefier motor. Speed of 360 RPM, so it's spinning relatively fast. And then that power, however much that 100 horsepower, is being transmitted through this gear set. We have N1 and N2 being number of teeth on gears. So that's telling us our gear ratio. You either need to know the number of teeth on these mating gears, or you need to know the diameters or the radius of the gears to know how fast one is spinning relative to the other one. So in this case, we know the number of teeth. And then we've got a gear A and gear B on this output shaft, the one at the top. And we want to find some diameters. We want to find angle of twist. And that looks like what we're trying to do. So let's see if we can figure out what we want here. So the first thing, the minimum satisfactory diameter for the motor shaft. So that's this shaft. That's the motor shaft. So that motor we're given a couple of things about it. It is spinning, the motor shaft is spinning at 360 revolutions per minute, so we know that. And it's delivering, or it says develops, so it's inputting to our system 100 horsepower. And what else do we know? All right, so we know this piece of information. The maximum shear stress in all the shafts is limited to 6,000 psi. So again, we know the tau max. All right, so that's what we know. Oh, made it too small. Let's try it again. Huh. Good enough. Good enough. All right. So let's look at our power equation first. Let's move this down some because it's kind of move it down here. All right. So power in the motor equals torque times omega. Now again, this is the internal torque, so technically I should be, cutting this thing open and finding the torque inside of it, but I'm actually going to use this equation to calculate the torque instead of like drawing a free body diagram and finding the torque like we did the previous 2 days. So they gave us 100 horsepower. Those units are going to need to be converted over to, I'm going to do inch-pounds per second. So 100 or 1 horsepower is equal to 6,600 inch-pound per second. So now we have inch-pounds per second on the left-hand side. Equals torque. That's what we want to find, is how much torque is in the yellow shaded motor shaft. Times omega, but they didn't give us omega, they gave us RPM. Oh, it's right there. 360 revolutions per minute. 1 minute is 60 seconds. And 1 revolution is 2 pi radians. Okay? So the only unknown in that equation is T, so we can solve for the torque. So this will be the torque in what I shaded in as the yellow motor shaft. If we can get our calculator to do us all this calculation. So 17,507, well, 0.04, and those units will be inch-pounds, the way I've got it set up. Let me just calculate it again to make sure. Okay, got the same number twice. Maybe we're doing it right. That's not what it wants, though. It wants the minimum, or the what did they say? Minimum satisfactory diameter. They did not say anything about a factor of safety. They just told us the largest shear stress that they're going to allow is 6,000 psi. So now we can go tau equals T. I'll use the C in this case. They want to know the outer diameter, but C is the outer radius, so we'll just remember that. So they have limited our tau to 6,000 pounds per square inch. The torque we just found out, C is the outer radius. We'll just put C in there. And J, again, this one doesn't say anything about being hollow, so we're going to use our, where'd I put them? There they are. I'm going to use this one that has the middle one here, pi over 2 times c to the fourth. Since I already have c in the equation, I'm going to use that one. So pi over 2 times c to the fourth. And so I've got c and c to the fourth becomes c cubed. And then the pounds, yeah, I'll end up with pounds per square inch again. Everything will work out unit wise. All right. So we have to solve for C. So this one I might need to do in some steps here to not confuse myself. 6,000. Let's multiply by pi over 2. Let's divide by 17,507.04. So I end up on the left-hand side with 0.5383 equals the right-hand side will be 1 over c cubed. So I'll need to use the reciprocal here to get c in the numerator. So 1 divided by 0.5383. So c cubed equals 1.8577 inches cubed, and therefore c is equal to, let's raise that to the 1/3 power, or take this cube root of it. I get, that's a really large number, 1.229, and that's inches. And remember, that is the radius, and they want the diameter. So let's see, 2.459 inch diameter. Does that make sense? We're doing 100 horsepower at 360 RPM. We're limited to a really kind of low shear stress, so maybe that's reasonable. Let's see, 2.459, see if WebWork cares for that number. Yep, 2.45853, yeah, that's 2.459, which is what we have. So we're good there. Okay, now it wants the same kind of thing, but the minimum satisfactory diameter for the power shaft. So the power shaft is that one. Power shaft is that. Motor shaft is yellow. So power shaft in this case is referring to the output power. So the yellow motor shaft would be the input power, and the cyan color would be output. So the difference here, so a couple of assumptions. Unless you're told that there's some efficiency loss, so this system is 85% efficient or something like that, then we're assuming that all of the input power, how much do all 100 horsepower input gets transmitted to the output. So all the 100 horsepower in the yellow shaft gets distributed to the cyan shaft. And that's unless we have some problem statement that includes the system is some percent efficient. In that case, which is more true in the real world, then if 100 horsepower goes in, we have an 80% efficient power transfer. Basically, that's between the two gears here. 80% efficient gear there. Then if we have 100 horsepower input, 80% efficiency, we have 80 horsepower in the cyan shaft. There might be some problems like that in the web work and possibly even on exam 3. But if it doesn't say anything about efficiency, then you're assuming that it's a 100% efficient process. All right. So, and this one doesn't say anything about efficiency, so we're assuming it's 100% efficient. Even though in the real world gear trains are not 100% efficient, we're going to assume that. Okay, so minimum satisfactory diameter for the power shaft. So the difference here is that it has the whole 100 horsepower of power going in the cyan shaft, so that's the same. We're going to find the torque. The difference is it's not spinning at the same rate. So the yellow shaft, motor shaft, is spinning at 360 RPM, but the gear ratio here between N1 and N2, the motor gear and the output shaft gear, is, for me, 85 to 10, so 8.5 to 1. So what that means is, if we look at it, you can see it here, but let's look at it from the end view. So there's the output motor shaft, the blue one. There's the input motor shaft, the yellow one. So the yellow gear is much larger diameter than the blue gear. And so if the yellow gear is spinning at 360 RPM, which is given in the problem statement, then the little gear is spinning much, much faster than that. It's going this way, isn't it? Based on the ratio. So this one had, 10 teeth? And this one had 85 teeth. And again, you might not be given teeth. You might be given the radius or the diameter. The ratios are all the same. Whether it's diameter, radius, or teeth, it's all the same ratio. So the little gear is spinning 8.5 times faster than the large gear. So 360 times 8.5 means it's spinning 3,060 RPM. So it's going much, much faster. The trade-off is that the torque that was being delivered by the yellow shaft, 17,000 inch-pounds, it is reduced by that same ratio. So speed is increased, smaller gear goes faster, but it has less torque in it. So we go from 17,507.04, divide that now by our gear ratio, 8.5, and the torque delivered by this yellow gear is 2,059.65, we'll say. That's inch-pounds. So it's the torque in the yellow one divided by our gear ratio. So it speeds up, but much less torque. And if you did it the other way, where the input gear is the small one and the output gear is the bigger one, then the output gear is not moving very fast, but you're multiplying the torque. So you have to, it's probably easiest to deal with the speeds first if you're relying on like intuition and what it looks like. It's probably easier to figure out the speed because you can kind of envision, maybe this thing's, here's 10 teeth. That's 3, 4, 5, 6, 7, 8, 9, 10. I have no idea if that's the right size spacing of this, but you have 10 teeth here, and they, I've got 10 teeth on this guy that go all the way around it. So every time 10 teeth of the large gear pass the smaller one has moved an entire revolution. The larger one has only moved an eighth of a revolution. So maybe it's easier to think about the speed ratios than it is to think about the torque ratios, and just know the torque is the inverse of the speed. So if I multiplied the speed, I divided the torque, and if I divided the speed, slowed it down, then I multiplied the torque. Okay, so there's our torque. hopefully, if we plug this number in, 2,059.65 inch-pounds. I don't actually need this equation. We're just writing it for writing it. The speed of 3,060 RPM, that ratio, or that equation, would also equal 100 horsepower. Now we'd have to convert our RPM over to radians per second. So 3060 divided by 60 times 2 times pi times 2,059.65 inch-pounds divided by 6,600 gives me 99.99989. So essentially 100 horsepower. So this is the same as what we did over here when we did power equals torque times omega. All right. So we don't really need this equation. What we need is this torque, because we're going to take the torque and tau equals T times C over J. Now, what it wants here, though, is the minimum satisfactory diameter for the power shaft. So we've got in section, well, in that section, the entire amount of torque is being transmitted. In the next section, between gear A and B, some of that torque has been used up, we'll say, by gear A, and there's less torque available for gear B. So the worst case scenario is the first line I drew, where it's between the N2 and gear A. So this one over here. So that same limit of 6,000 pounds per square inch is in effect, because they said the shear stress in these shafts, so all of them, must be limited to 6,000 psi. The torque in that section is 2,059.65 inch-pounds. Well, we don't know. We want to find the diameter, so C. And I'm going to use that pi over 2 times C to the 4th again. So cancel that C out, cancel one of those out. We've got C cubed. 6,000 times pi over 2 divided by 2059.65, and I get 4.5759 equals 1 over C cubed. So 1 divided by 4.5759, C cubed is equal to 0.2185, and that means C is equal to 0.602 inches. And we actually want the diameter, so multiply times 2. So OD for the output shaft is 1.205 inches. And hopefully WebWork agrees. Oh, I didn't want the, don't need that. 1.204, yes. Okay. I have 1.205, so they had 1.2046. Actually, that's what I did have, so good enough. All right. The last part, we might as well do that because that'll do angle of twist. I think that'll probably give us enough experience with the shafts. So we'll do this angle of twist, and that should be enough for today. So what it wants is the angle of twist between gear B and the 10-tooth gear, assuming the whole shaft has the same diameter and is composed of annealed red brass. So we'll have to go get the modulus of rigidity, or otherwise known as the shear modulus, for annealed red brass, because I don't know that. Okay, so what that is, that would, let's just draw us a little picture down here somewhere. So here's the gear that is the 10-tooth gear on the end of the shaft. And then we've got gear A. Doesn't really matter how many teeth it has, because we're not interested in that part. And then we've got gear B. And this section, that yellow section, is twisting some amount. Even though it's spinning, it's twisting. And this section is twisting some amount, even though it's spinning. And we want to know what's the total angle of twist from, we'll just call this one N because it was N2, I think, in our picture. So from N to B, what is the total amount of twist? So angle of twist equation, theta equals torque times length over polar moment of inertia times modulus of rigidity. Let's go find that modulus of rigidity before we get too far. Let's see. It was annealed red brass. We're in US units. Let's find it. All right, let's zoom in. So, red brass annealed, the next to last column. So, 5.6, the units on that are 1,000 KSI, so that's 5.6 million PSI. Okay. So, G, 5.6 times 10 to the 6th PSI. We're going to need the length of these sections. So let's see. The section from N to A is labeled B. 7 feet. Okay. The length from A to B is labeled C. 3 feet. Okay. And angle of twist between gear B and the 10-tooth gear. Okay. It has the same diameter, the diameter that we just calculated, 1.205 inches. So we'll say OD 1.205 inch diameter shaft made out of the annealed red brass. The torque, all right? So the torque in this section, if I draw this little free body diagram, I've got an input torque here. I don't know which way it's going, but I've got, some direction. That one was the 2,059.65 inch-pounds. And so the inner torque for that section, the yellow section, is also 2,059.65 inch-pounds. Okay, so we can figure out the angle of twist for that section. Theta equals 2,000. Let me make sure that number is right. 2,059.65. The length of that section is 7 feet. I'm going to convert that over 12 inches per foot. We found its outer diameter, so pi over 32 times 1.205 inches to the fourth. And then we just looked up the modulus of rigidity, 5.6 times 10 to the 6th PSI. So that all those units should cancel out for us. And then we can find the radians that the yellow piece of this shaft twist. That is not the same yellow that I started out. I should have used a different color. For some reason I switched them up. So just this one. Look at this picture. Alright, so 2059.65 times 7 times 12. So our numerator is 173,010.6 Now our denominator, 1.205 to the fourth times pi divided by 32 times 5,600,000. Denominator is 1,159,140.58. All right, so 173,010.6 divided by 1159140.58. Whoops. 58 is 0.1493 radians. Or, if you want that in degrees, multiply by 180 and divide by pi. 8.55 degrees. That's just the yellow section, though. The purple magenta section is also twisting. So it has a different torque, though. So we have to know something about, let's see. It says over here, A and B deliver 40 and 60 horsepower. So 40 horsepower is being used there. 60 horsepower is being used there, right? A is 40, yes. So of our 100, and that also shows you that we're assuming this is 100% efficient. We have 100 horsepower in and from the motor and 100 horsepower out from the power shaft. We've got to figure out how much torque is being used in that 40 horsepower. I put pounds. Okay, so let's do power equals torque times omega, and let's just do the 60 horsepower because that'll be how much torque is having to be delivered in the magenta section. So basically I'm going to cut it open here, and we could do the 40, I guess, and subtract. We could do that either way. Maybe we'll do that. That might make more sense. Alright, so 40 horsepower times 6,600 inch-pounds per second per horsepower equals some amount of torque times omega. This whole shaft is spinning at the same speed, and that speed I've already forgotten. Where's it at? 3060 RPM. One minute is 60 seconds. One revolution is 2 pi radians. Move that so it's not like jammed up against that other thing. So we can solve for torque here. Okay, so let's see, 40 times 6,600 divided by 3060 times 60 divided by 2 divided by pi. So the torque, let's see, did I do everything there? I think so. 823.86, those would be inch-pounds. So I had 2,059.65 inch-pounds. We can see that right above this equation. The gear A, we'll say used up. That's probably not the best word, but it might help you think about it the right way. So it used up 800 of those. So 2059.65 minus 823.86. So the magenta section, section AB, has the torque in AB is equal to 2,059.65 inch-pounds minus 823.86 inch-pounds, which equals 1,235.79 inch-pounds. And if we had done what I was originally going to say to do, where we just do the 60 horsepower, then we would have calculated this number, 1,235.79. Okay, so theta, this is into A. Now let's draw our second free body diagram here for the finding out the torque. There's the 10-tooth gear. Here's gear A. Here's the shaft coming off of gear A, and we have 2,059.65 inch-pounds here. Whoops. We have 823.86 inch-pounds here. Oh wait, going the other way though. I drew it the wrong way. Let's go that way. And then that leaves our 1,235.79 inch-pounds. So that's the diagram of the equation we just wrote. And this arrow is the same direction as this arrow. So that means that the two angles of twist, the one for the yellow section and the one for the magenta section, are going to add together. All right, so theta for this will be section AB equals the torque 1,235.79 inch-pounds times the length of section AB, which is 3 feet, 12 inches per foot. And the denominator is the exact same. I wish, oh, well, it's that same 1,159,140.58. Same number as before, because it's the same material and the same size cross section. So 1,235.79 times 3 times 12 divided by 1,159,140.58 is a smaller number, 0.0384 radians, which, if you want degrees, multiply times 180 and divide by pi. 2.199 degrees. I don't know what it wants the answers in. It wants the answers in degrees. So we should add the 8.55 from previous, and our total angle of twist is 10.75 degrees. That seems like a lot, but let's check web work. Well, they have 10.76. We have 10.75. Probably good enough for web work. Good enough for me. All right, so that's kind of a little bit of everything. Torsional shear stress, angle of twist, and power transmission, with some gear ratio ideas thrown in there, right here. All of the homework should be open. I reopened quiz 4. Not everybody had finished it, so quiz 4 is open a little bit. I think I might have to extend lab 2's deadline. I haven't checked on that, so I might have to extend that a couple of days. We're getting close to where there's not that many days left. Next Monday is the redo. So if you want to redo exam 1 or exam 2, that is Monday. So that's getting close. Wednesday is exam 3, which is the last exam. And then Thursday is just kind of turning everything in, mainly the group project. I have seen in Discord several people trying to arrange groups. That's good. I've gotten maybe 2 or 3 emails of people who have arranged groups. That probably leaves a lot of people out there needing to sort out a group. So don't wait too long to do that, because we don't have long left in the quarter. All right, I don't see anything in the chat question-wise, so I think we'll be back Wednesday, and we'll do pressure vessels. They're a one-day thing. These are thin-walled pressure vessels, I should say that. They're a pretty simple, straightforward topic. We should be able to cover that all on Wednesday. Thursday will be stress concentrations by hand, and that's it. That's all the content for the whole quarter. And the rest